Hello, I'm Paul Beckwith. I'm with the University of Ottawa Laboratory for Paleoclimatology and with Carleton University Department of Geography and Environmental Studies. And I'm talking about methane, a recent paper that has just come out assessing the science of methane release from methane clathrates. So what we see here is this is at the bottom of the seafloor, what we see is calcium rock here with all the mussels growing here, and we have this white ice-like material which is the methane hydrate. So the methane has actually seeped through the seafloor, and because of the high pressures down at this depth and the low temperatures, it forms these methane hydrates here. And this is on the seafloor of the Gulf of Mexico. It's photographed by NOAA's remotely operated vehicle in 2014. It's not thought that seafloor gas hydrates are a large enough volume within the total global reservoir, but their existence on the seafloor at these depths shows that the hydrates can be formed by gases, methane migrating across the sediment water interface and then interacting with the ocean water. So what is interesting is that methane hydrate, so the methane molecule is trapped in a cage of frozen ice, frozen water molecules. 1 cubic meter of the gas hydrate, when it melts and dissociates, it releases 180 cubic meters of methane. And so this large increase can put a lot of pressure, as the thawing goes on. If it's in the sediments, it builds up a lot of pressure, and that pressure can build up and then basically raise the surface of the seafloor, and it can actually cause craters to appear as it ejects material and is released quickly. So the big concern is, what is the risk of this happening on a catastrophic basis over a very large area? So basically, the stability of the methane requires pressures to be high and low temperatures to be low. So when you go down deeper into the ocean, you get those conditions. So basically 300 to 600 meters roughly. This is about 1,000 feet. This is about 2,000 feet. This sort of depth, 300 meters, would be occurring in northerly regions, say in the Arctic, where the water temperature is lower. This type of number, 600 meters, would be closer to the equatorial regions, where the water temperature at the surface is higher, so you have to go down deeper to get the temperature low enough and the pressure high enough to have hydrates being stable. And this is the gas hydrate stability zone. It doesn't mean that the gas is there, but it means if the methane gas is there, there's a source of it somewhere, then the methane will be trapped in these hydrates. So there's a couple things that happen. If ocean temperatures rise, then that can thaw out the hydrates. And if pressure is lowered, then that will also release methane. So what is interesting is right now the oceans are warming very rapidly with abrupt climate change, and this is making the hydrates in the ocean more susceptible to release. But also, by the same token, the sea level is rising, and the more rapidly the sea level rises, that reduces the likelihood of large releases of methane hydrates from the seafloor, because that additional pressure keeps them more stable. So it's competing processes there. So there's large amounts of carbon in these hydrates, and there's various estimates of what percentage of the Earth's total the numbers vary from about half of the Earth's total to about 15% of the Earth's total mobile carbon, which includes carbon in soils, land biota, so trees, plants and animals, flora and fauna, fossil fuels, peat, and other reservoirs. So these are vast amounts of methane, and so it's actually surprising that we don't know a hell of a lot more about them than we do. But we're on a steep learning curve right now. So this is showing some hydrate. This is a map, and this is showing the hydrate stability zone thickness on various points. So here it's in the red areas up to 900 meters. In the yellow areas, something like 450 to 750 meters. That's the thickness of the hydrate stability zone. And as you go into large areas of the ocean basins, you get smaller numbers. The red dots are where measurements have been made of the thickness, and the blue dots are where so red is locations of known, where are we here? I've lost my, blue circles, red circles, recovered samples, photographs in those regions, and the blue ones are inferred from well logs, geophysical markers, seismic studies, etc., but not recovered samples in those regions. Okay, so we've got good maps of where the hydrates are located on the seafloor. Now, this is showing what conditions are required for the hydrates. So if you're near the surface, this is the surface of the water, this is depth of the water in permafrost, and this is in the seafloor sediments. So the depths below this, the seafloor, if this would be the water column, this would be the seafloor, this would be in the sediments here. So first of all, in this case, near the surface you have free gas. As you go deeper, you have the permafrost, and you have water, ice, and gas hydrates can be in these regions. This is meters below the surface. And then this is regions where you just have the gas hydrates existing. And then below there, because of the geothermal gradient, it's warming as you go deeper and deeper. You would just have free gas here, so free methane. So this methane, if there's a passageway to the surface, this could rise up to the surface, but it's generally trapped under frozen ground in other sections. Now on the seafloor, this is the ocean water temperature dropping with depth. This is the phase boundary, in which case you have frozen stuff here and you have gases here. So free gas is possible here. In this case, down. So you have you have the sediments here of the seafloor. So the gas hydrates are in this location here, and then because of the geothermal gradient, you get free gas underneath, and basically, when you increase the temperature, then the solubility of the methane is also increasing, and so there's more methane that's in the water column, and so basically, there's a lot of different factors that come into play that determine how much methane is in the sediment, how much goes into the water column, and the processes that happen within those mediums, and how much gets up into the atmosphere. Okay, so this is showing that if you increase the bottom water temperature, then the depth below the seafloor. So this is this is at the top of the sediment. This is as you go deeper and deeper into the mud and sediments. And what happens is there's a stability curve, and as the ocean temperature rises, I believe that's about a 5. So this is about a, this distance here is about half of 5 degrees or so. The length of this arrow, about halfway between those notches here. So as the temperature is rising, the curve is rising, and the depth in the sediments at which the you have stability changes. It's the stability zone is changing, and so as the water temperature rises and the heat goes through the sediments and things, then it's going to dissociate the hydrates that are closer to the interface, the mud water interface. So, if you increase sea level, then it increases the pressure and it moves you lower down. So it's less likely to get dissociation of the hydrate. So how much methane is stored in these gas hydrates? Now, that's an important question, and the number has changed over the years. So some of the original work, 1988, Caven Volda, in this paper, there was an estimate of 11,000 gigatons of gas hydrates, of methane in gas hydrates. Fossil fuels being less than half of that, lots in the soils, dissolved in the land, in the peat, and various sources, but loads in the hydrates. More recent papers have reduced that number. Okay, this large number assumed that in the pores in the gas hydrate stability zone there was loads of methane there. But the case is you can have this zone and you have to have a source of methane, and even though the conditions are set that hydrates would be stable, if there was no source and there's no hydrates there. So that's reduced this number. So the accepted current number is closer to 1,800. So this is very good news. Much less methane hydrates around the planet if this number is more accurate. So where is this number coming from? So the 11,000 gigaton estimate was made soon after the first dedicated drilling programs, and then, but other reports more recently have. Where are we here? Okay, I think we're up here. Okay, no. Okay, so more recent estimates in 2011. There was an estimate in 2004, this estimate in 2011, another one in 2013, and there was some variation in these numbers, but if you take the whole literature, these main papers and other ones, then you get a number closer to the 1,800. So this is a very significant thing. If you see these numbers still quoted, then these numbers aren't the current thinking on the total gigatons of carbon in the gas hydrates. Okay, right now, in terms of the sources of methane, agriculture and wetlands are big chunks, biomass burning, fossil fuels, large chunks. The amount actually coming from gas hydrates and permafrost is actually quite small, but these numbers are rapidly growing as the Arctic is warming. There's also methane from termites, wildfires, incomplete combustion, wild animals, freshwater sources, geological sources. Okay, so there's a whole bunch of different sources, and those, so that puts the methane emission rate from the hydrates sort of in perspective.